We can measure the properties of substances related to heat, and one property is called heat capacity. Heat capacity has the abbreviation capital C. We have a lot of different units here that have a C in them, or they start with a C, so please try not to get them confused. Little CAL is calories. Capital CAL is kilocalories, or big C calories. Just a plain old capital C is heat capacity. And we'll talk on the next slide about one with a lowercase c, which is specific heat. Additionally, degrees Celsius is also a capital C, but it has the degree symbol next to it. If it has a degree symbol next to it, it's a unit of temperature, which is Celsius. If it does not have the degree symbol next to it, then it's heat capacity. Heat capacity is defined as the amount of heat that a body of matter absorbs or releases when it experiences a temperature change. In other words, delta T, of 1 degree Celsius. Delta is a symbol that we use for change, so delta T is a change in temperature. Remember, we use Q as the symbol for heat. We can write the definition of heat capacity in equation form. Capital C, heat capacity, equals Q, quantity of heat, over delta T, change in temperature. The change in temperature is always final temperature minus initial temperature. We can have two different pans and heat them up with a temperature change of 50 degrees Celsius. Let's say it started out at 25 Celsius and went up to 75 Celsius. 75 minus 25 equals a 50 degree temperature change. Let's say we heated it up by 50 degrees and measured the amount of energy needed to do that. For the small pan, it only needed 18,140 joules to make that temperature change for that pan. For the large pan, it needed 90,700 joules for that same temperature change, because the larger pan has more mass to heat up. The heat capacity of the small pan is 363 joules per degree Celsius, whereas for the large pan, it's 1,814 joules per degree Celsius. The small pan has the smaller heat capacity, and the larger pan has the larger heat capacity. Think of heat capacity as the ability to hold heat or store heat. The larger pan can store more heat. Specific heat, on the other hand, we represent with a small c. It's defined as the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. For heat capacity, we're raising the whole substance, the whole pan, for example, by 1 degree Celsius. But with specific heat, we're only heating up 1 gram of each substance. 1 gram out of the small pan, or 1 gram out of the large pan. Since it's just 1 gram of each, it's going to be the same value for each of them, as long as the pans are made of the same material as each other. The specific heat equation is similar to the heat capacity equation, except it includes mass. You need to know the mass of the object in order to find the heat needed for 1 gram of the substance. We're going to take the quantity of heat, Q, that is put into heating up the pan, and divide it by the mass of the pan and the temperature change. For the small pan, we have a small amount of heat on the top, 18,140 joules, and a small mass on the bottom, 808 grams. And the temperature change is the same for both pans, 50 degrees Celsius. For the large pan, we have a large heat on top, 90,700 joules, and a large mass on the bottom, 4,040 grams, and the same 50 degrees Celsius. When we do the calculation, it ends up being the same amount for both pans, 0.449 joules per gram Celsius. Specific heat is a constant for any particular type of substance. So water will have a particular specific heat, iron will have a different specific heat, steel would have its own specific heat. All sorts of things have a constant specific heat. We can look up specific heats in a table such as this one. This table is in your slides for you to reference as you're doing your homework problems. There are a variety of different specific heats listed. Some of them are just single elements like helium. Some of them are compounds like water. Each pure substance has its own specific heat. The state of matter is important for specific heat. For example, liquid water has a specific heat of 4.94, whereas ice, solid water, has a specific heat of 2.093. The specific heats in this table are measured at 1 bar of pressure and 25 degrees Celsius. At different pressures and temperatures, the values might be slightly different. Anytime we have an equation with multiple variables in it, we can rearrange it to solve for any of those variables. One of the variables that we're often going to be interested in finding is heat, Q. We can rearrange the equation for specific heat to solve for Q by multiplying both sides by m times delta T. The rearranged equation is Q equals mc delta T. I remember this equation because it looks a lot like MCAT, the test that students take as they're preparing to enter medical school. Delta is not the same thing as A. They look pretty similar. In this equation, delta T is change in temperature, which is always final minus initial, not the other way around. It's going to be really important that you do it in the correct order. We can plug T final minus T initial into our equation instead of delta T. So the equation becomes Q equals mc times T final minus T initial. There are 5 different items we could solve for in this equation. We could solve for Q, M, C, T final, or T initial, as long as we know all the other variables besides the one we're trying to solve for. Here's an example where we're trying to calculate an amount of heat. We have a flask containing 8 times 10 to the 2 grams of water, and it's heated, so the temperature increases from 21 degrees Celsius to 85 degrees Celsius. That means the initial temperature is 21 and the final temperature is 85. The question is asking how much heat the water absorbed. We're going to use specific heat of liquid water, which is 4.184 joules per gram Celsius. We plug what we know into our equation, Q equals mc delta T, or in other words, Q equals mc times T final minus T initial. We plug in 8 times 10 to the 2 grams as the mass of the water that's heated. We plug in the specific heat of water, which is 4.184 joules per gram Celsius. We plug in our 2 temperatures, final minus initial. It ended up at 85, so we list that first, and it started out at 21, so we list that second. We'll do 85 minus 21. Notice the units end up canceling out. So grams of water cancel out with grams in the denominator of a specific heat. The degrees Celsius in the denominator of the specific heat cancel out with the degrees Celsius in the temperatures, and we're left with joules, which is a common unit for heat. Remember, energy takes the form of heat or work. Since heat is a form of energy, it uses energy units, such as joules. When we plug in all of our numbers and do the calculation, we come out with 214,221 joules as how much heat the water absorbed. We could put this into scientific notation just to make the number a little bit more manageable. So we could write it as 2.1 times 10 to the 5th joules. Or we could put it into kilojoules and write it as 2.1 times 10 to the 2 kilojoules. We'll often change from joules to kilojoules just so we can get a smaller value for our number. The sign on the Q is important. It's related to whether the heat is absorbed or released. Since Q is positive here, that tells us that heat is going in. It's being added to the substance. In this case, Q is being added to the water. The water is absorbing heat. Calculate the amount of heat required to heat 725 grams of water from 22.1 degrees Celsius to 110.5 degrees Celsius. The specific heat of water is 4.184 joules per gram Celsius. Is it A, negative 64.1 kilojoules, B, 15.3 kilojoules, C, 268.2 kilojoules, or D, 0.51 kilojoules? The correct answer is C, 268.2 kilojoules. You're using the equation Q equals mc delta T. M is your mass of 725 grams, C is the specific heat of water, which is 4.184 joules per gram Celsius, and delta T, which is T final minus T initial, is 110.5 minus 22.1. You should end up calculating it as 268,153 joules, which is the same thing as 268.2 kilojoules.